Example 3 says use integration to find the formula for the volume of a sphere with radius r. Now here in the picture we have graphed a circle, and it's not quite a sphere because it's graphed in 2 dimensions on the xy plane, but what's going to help us is we can think about this as a circle of radius r. So this x-intercept here is negative r comma 0. And this x-intercept here is r comma 0. And I want to kind of picture and imagine that this is a three-dimensional shape. And so if I were to take a cross-section, notice that this is different than our last example with the cylinder because our cross-sections are not the same sizes and they are variable or dynamic. So I'm just going to pick some arbitrary place, and I'm going to take a cross-section. So if I sliced into my sphere here, and I looked at that two-dimensional face, that's going to give me a circle. And if I kind of cut this and make it into a three-dimensional piece, then the thickness of this slice of bread, so imagine we have this spherical loaf of bread and we slice into it, and so this thin kind of slice of bread here, it is a circular cylinder and it has a thickness of delta x, and I essentially need to figure out what is the radius of this particular slice or any arbitrary slice. And so the radius is the distance from my x-axis to a point on the circle. So it would probably be helpful if we came up with a formula for this circle, or come up with an equation for this circle. So from a previous math class, you might recall that the general form of a circle is x minus h squared plus y minus k squared is equal to the radius squared. And h and k help us to identify the center of our circle. And remember, we're looking at the blue circle right now, so our center is located at the origin 0, 0, that's going to tell us that h is 0 and k is 0. So our formula ultimately boils down to x squared plus y squared is equal to, and then the radius squared. And we know here just that the radius is r, so I'm just going to have this be r squared. Now, really, if you come back to this disk, this like circular disk, the radius of it is the y value. It's the distance between the x-axis and the point on our blue circle, which is another way of saying the y value. So what we can do is we can take this equation here and we can solve it for y. I can subtract both sides by x squared. And if I take the square root of both sides, I get y equals plus or minus the square root of r squared minus x squared. Now, hopefully you remember from a pre-calculus class that we get plus or minus because a circle is not a function. It does not pass the vertical line test. So the positive part of this equation gives us the upper half of our circle, and the negative part gives us the lower half of our circle, because if I have negative square root of something, that means that all of my y values would be negative and therefore below the x-axis. So I'm just going to go ahead and say here that the y value we really care about is y equals positive square root of r squared minus x squared. And now this is going to help us to be able to come up with our volume for this sphere. So I want to come up with a definite integral that's going to help us to find the entire volume of this sphere. And remember from the previous video that the way that we are finding the volume is we're thinking about this three-dimensional shape like a loaf of bread. And what we're doing is we're slicing up our loaf of bread into slices, calculating the volumes of those slices and adding them together. So if I were to create these slices, my leftmost slice, or my starting slice, kind of starts at the value of negative r along perpendicular to the x-axis. So when I'm creating my definite integral to have my volume equal this definite integral, my lower limit of integration is going to be negative r. And if I continue to draw these circular cylinder slices of bread, they're going to keep going until I reach the very end. And my last slice, they kind of stop at x equals r. So that's going to be my upper limit of integration is positive r. And then the thing that we're integrating, our integrand, should be the volume of each of these slices of bread. So we know that for a circular cylinder, the volume of that we saw previously was pi times the radius, which we said that the radius was the y value, and y, because we are going to end up integrating with respect to x, let's replace it with this expression here. So it's going to be the square root of r squared minus x squared. And again, the volume of a circular cylinder is pi times the radius squared, and then times the height. And in this case, our height is delta x, which gets changed to dx when we are writing it in the definite integral form. Now, something that you might notice is the circle that we have drawn here is symmetric across the y-axis. And so something that's going to make our life a little bit easier is if we use the symmetry properties that we learned about before. And so I can actually change my limits of integration to be from 0 to r. I just have to double the value that I get from the definite integral. And I'm also going to factor out pi. So on the outside of my integral, I have 2 pi. And then if I square this expression, we're going to end up getting just r squared minus x squared dx. So let's go ahead and integrate that. Remember that, keep in mind, we are integrating with respect to x. And in this particular question, r is a constant. R is not changing. So keep that in mind as we're integrating. We have 2 pi, and then the antiderivative is r squared times x minus x cubed over 3. From x equals 0 to x equals r. And if we evaluate it at 0, it's just going to change into 0. So we just need to plug in r. So we get r squared times r minus r cubed over 3. And again, if we were to plug in 0, we would just get 0. Okay, so we still have this 2 pi on the outside, and r squared times r gives us r cubed. I am going to multiply this by 3 over 3 so that I get a common denominator. And we get 2 pi times 2r cubed over 3. And then if we multiply those together, we get 4 pi r cubed over 3. And so this is the volume of a sphere with radius r. And this matches up with what you might have learned in geometry for the volume of a sphere. So that's cool that we were essentially able to derive this volume formula that you might have learned in geometry now using calculus. Now we are going to look at solids of revolutions. They are obtained by revolving a region around a line. If the line of rotation is horizontal, then we use the formula the volume equals the definite integral from a to b of a of x times dx. If the line of rotation is vertical, then we use the formula v equals the definite integral from c to d of a of y times dy. In the revolution, the cross-section is either a disk or a circle with area pi times the radius squared, or a washer, which is a circle with a hole in the center with area equal to pi times the outer radius squared minus pi times the inner radius squared, which I've kind of used this shorthand notation, which this is not a standard notation, but I've factored out pi and just kind of abbreviated it as the pi times the outer radius squared minus the inner radius squared. So let's look at an example. Example 4 says, find the volume of the solid that is obtained when the region under the curve y equals the square root of x is revolved about the x-axis bounded by x equals 1 and x equals 4. It's going to be helpful if we start off by graphing the scenario that's described here. So here is my y-axis, here is my x-axis, and I want to look at the graph of y equals the square root of x, which looks something like that. However, I'm only looking at the region bounded by y equals the square root of x, the x-axis, and also bounded by x equals 1 and x equals 4. So I'm going to go ahead and erase this graph that I had started because I only want to look at between x equals 1 and x equals 4. So my graph is going to look something like that. And again, this is the graph of y equals the square root of x. And we're bounded by the x-axis, that curve y equals the square root of x, and the two vertical lines x equals 1 and x equals 4. So if I were to shade the region that is bounded, and remember bounded means enclosed, so the enclosed space that we're looking at is this space here, or that region. And what I want to do is I want to take that two-dimensional region and we want to rotate it about the x-axis. So I'm going to use this little notation as an indication that we are rotating this region. And when we do that, when we rotate about the x-axis, if we swoop that region around, what it does is it creates this three-dimensional shape. And it almost looks like a sideways flower pot that is solid in the middle, and that's our essentially loaf of bread in this scenario. So I'm going to go ahead and include a much nicer graph or drawing than the one that I have here. So I've now included this thing where I've revolved the region, the two-dimensional region we were looking at, about the x-axis, and I get this three-dimensional shape now, and it kind of looks like a sideways flower pot. And remember, we are thinking of this like a slice of bread, and so I can cut this anywhere, and if I cut this here, I'm getting this circular cylinder shape of a slice of bread. And I want to know the radius, and I know that the thickness is delta x. And the radius of this thing is the distance from the x-axis to the point on the curve there. So I've gone ahead and I've extrapolated this cross-section / disk, and I'm going to add some thickness to it, so that it looks more like a three-dimensional shape. And again, this thickness is delta x, and the radius, because we're measuring the distance from the x-axis to that point on the curve, the radius is just the square root of x, where x is whatever this x value is. I just chose some arbitrary point to draw my cross-section, so x could be 2, it could be 3, really any number between x equals 1 and x equals 4. So what I want to do now again is I want to create the volume, and my leftmost cross-section is going to be here, starting at x equals 1, and then my last cross-section here, my last slice of bread, is going to end here at x equals 4. So that's going to help us with our limits of integration when we're setting up our definite integral. So our volume is equal to the definite integral. I'm going to write kind of like a general formula. So we're integrating from a to b, and we have pi times the radius squared times the thickness, which is dx here. So we said earlier my lower limit of integration is 1. My upper limit of integration is 4, and I can square the radius, which we established here. That distance is the square root of x. So I have pi times the square root of x, quantity squared, dx. And pi is a constant, so I can factor that out of my integral. And my integrand is going to simplify to x times dx. At this point, we can just integrate. So I have pi times x squared over 2, and I'm evaluating this from x equals 1 to x equals 4. And then if I have 4 squared over 2 minus 1 squared over 2, we get pi times 16 over 2 is 8 minus 1/2, and that will simplify to 15 pi over 2. And so that represents the volume of this three-dimensional shape.